Welcome to Calculus. Today we will investigate using the first derivative test to find local extrema, so local maxima or local minima. So for our first function, we have this cubic f of x equals x cubed plus 6 squared, x squared plus 12x plus 1. And we want to do two tasks for this, for each of our functions. First, we want to find the critical numbers. And then we want to use the first derivative test to find any local extrema. So we'll find the critical numbers first. Remember, to find a critical number, I'm looking for the c, which is a value in the domain of the function, for which the slope of a tangent line at c equals 0. So I want to take the derivative of the original and then set it equal to 0 and solve. So we'll do that first. So the derivative of f of x for this polynomial function is going to be 3x squared plus 12x plus 12. And once I have the derivative, again, I want to solve it for 0. So I see that when I set this equal to 0, I can divide a 3 out of each term. And then I want to see if I can factor this once I've divided that 3 out. So I have the quadratic x squared plus 4x plus 4 equals 0. And I'm in luck, that was going to factor well as x plus 2 times x plus 2. 2 times 2 equals 4. 2 plus 2 equals 4. And then when I solve that, I got two identical solutions. Since these are both x plus 2, I would subtract 2 from each side. And to get the solution, which is my critical number here of x equals -2. So I'm going to label that. That's my critical number. So remember, what a critical number tells us is that either the value of the derivative at -2 equals 0, or it does not exist. So we need to figure out at this point how to interpret what that critical number represents. Is it a maximum? Is it a minimum? Or is it neither? Is it some sort of inflection point or asymptote? Well, that leads us to our first derivative test. So let's say what the first derivative test tells us in terms of information about a function's extrema. So here we go. This is the statement of the first derivative test. So if c is a critical number, of a function f of x on the interval a to b, and f of x is continuous on the interval from a to b, we really have three parts to the conclusion. If the value of the derivative, so f prime at x, changes from positive to negative at c, c is a local maximum. That's one of the cases. Another case is if the value of the derivative of the function changes from negative to positive at c. C is a local minimum. Good. And then there's a final case, see if you can predict it, and if the value of the derivative you've got, it does not change at c. C is neither a local max nor a local min. And so really what we're looking for with the first derivative test is what's happening to the y values of the derivative near the critical number. So let's go ahead and grab a table of values for our derivative. So I'm going to look at the derivative specifically. So here's x, f prime of x. And I want to center that -2. So I'm going to give -4, -3, -2, and then we'll go to -1 and 0. So I've calculated these out for this derivative function. At -4, the value of this function is going to be 12. At -3, the value is +3. At -2, our actual critical number, we already know that that's going to be 0. At -1, the value is 3, so we see that symmetry of the quadratic, and then we could probably predict output at 0 is 12 again. So once I have those values, I just want to highlight where the critical number is. It's -2, and we just need to note what's the sign of the y values previous to -2, and how does it compare with the sign of the y values after -2 to the right of -2. And what we're seeing for this case is that the sign is positive before. 12 and 3 are both positive. 3 and 12 are positive. So then the case that we are observing here is this last case. F of x, the sign of the derivative does not change at c. And so what we would say is c is neither a maximum nor a minimum. Why is that the case? So looking at the graph of the function's pretty informative here. Let's just jump really quickly to Desmos to see how this function and its derivative interact. So the original functions f of x equals x cubed plus 6x squared plus 12x plus 1. So there's our original function. The derivative we can plot as well is 3x squared. This is the quadratic plus 12x plus 12. And so if we change our view a little bit, zoom out a little bit, we have a view of those two functions. So the purple is the original, the parabola here in black is the derivative. And so what we're saying is that the value of the function here at -2, so I can pick that out there on the purple original curve, is neither a maximum nor a minimum. And that looks about right for the curve. That's not the lowest point, that's not the highest point, even in a local area. And so what we're seeing is that it's not either of those. What we would call this is an inflection point. It's a change in concavity. But again, that is all falling into line with what we saw with the algebra on our notes. And so our answer here is that C is neither max nor min. So we'll circle our answer there and just finalize neither max nor minimum. It's an inflection point. All right. So our first example here is a polynomial function, a cubic function, and we use first derivative test to find that inflection point. Let's take a look at a quotient function. So here is f of x equals natural log of x over x cubed. Again, I want to start off by finding what are the critical numbers. So I want to find the derivative of this function. And since it is a fraction and I got variables in the numerator and the denominator, I can use the quotient rule. So remember, that's considering the numerator function to be f of x, denominator function g of x. So it starts g of x, so x cubed, times the derivative of f of x, so that's derivative of natural log is 1 over x, minus the f function, natural log of x, times the derivative of g, 3x squared, all over g squared, so that's x cubed squared. So we'll simplify that expression. So x cubed times 1 over x is going to be x squared minus 3x squared times natural log of x. I'll just invert the order there, over x to the power of 6. But then I've got these powers of x that can be canceled. So that's going to give us final version here for the derivative of f of x of 1 minus 3 natural log of x over x to the power of 4. Now, again, with the derivative, what I want to do is set that equal to 0 and solve. Now, since this is a quotient, I have two considerations I need to make. From the numerator, if the numerator equals 0, then that's an actual critical point, which could be a maximum or a minimum. So let's deal with that first. So from the numerator, we have this equation 1 minus 3 times natural log of x equals 0. And we'll solve that. So I'm going to subtract 1 both sides. And we get negative 3 times natural log of x equals negative 1. Then I'm going to divide by negative 3. And we see that the natural log of x equals 1/3. And then I need to convert this to an exponential, and that'll really solve this for me. Remember, natural log is log base e of x. And if I were to convert that to an exponential statement, it's e to the power of 1/3 equals x. And the value of e to the power of 1/3, you can imagine it's smaller than just e. So e to the power of 1/3 of the cube root of e is 1.396 roughly. So that's one possible critical number. The other one is if I went back to the fraction and considered now the denominator. So the denominator equaling 0 would not be a maximum or a minimum, but it could be an asymptote. So let me set that one equal to 0 as well. And that solves pretty quickly. X to the 4th equals 0, ... x equals 0. So we've got these two critical points, e to the power of 1/3 and 0. So what we need to do is look at the table for the derivative here, and then we can interpret based on how the signs change. So here's x and the derivative of f of x. And the values that we'll pick here, let's do -1, 0, 1. We'll put e to the power of 1/3. Again, that's got the value of about 1.396. And then 2, 3, and that's enough for us to see. So again, we're just looking for what is the sign change. So at -1, it's undefined. It's also undefined at 0. And then at 1, we have a value of 1. E to the power of 1/3 is 0. 2 is negative 0.07. 3 is negative 0.03. And so for both of our numbers, we can make a claim here. If I find my 0, that was my denominator value, I see that the sign it's really kind of the trivial case. It's undefined, so it could be plus or minus, we don't know. 0 itself is undefined, 1 is positive. This is not a maximum, and it's not a minimum. In fact, what we'll see here is on the graph, this is an asymptote. Now, for the other value, e to the power of 1/3, we see that that has the value of 0. So before e to the power of a third, 1 had the value of 1, which was positive. And then after e to the power of 1/3, 2 had the power sign negative, so did 3. And so we're going from positive to negative, and that's going to be indicative of a local maximum. Again, according to our definition of the first derivative test, if I change from a positive sign to a negative sign, as I go from left to right, that's a local maximum. Again, what we can do is just confirm our analysis here by looking at the graph. So let's just really quickly take a look at the graph of the original function here and its derivative. So f of x equals natural log of x over x cubed. So there's the original function. Here's the derivative, which we calculated to be 1 minus 3 times natural log of x over x to the power of 4. And if I were to zoom in slightly, and we can also just zoom in slightly so we can see what's going on here for this function and its derivative. So again, the original function's in red, the derivative's in blue. If I type in the critical number at e to the power of 1/3, I can definitely see there that the original function has a maximum critical point right there at x value e to the power of 1/3. And that's corresponding with the derivative having a 0, changing from positive value to negative value. So we'll just head back to the notes screen. Again, the graphical consideration can give us confirmation of what we're seeing with the algebra here. So we've looked at a polynomial, we've looked at a quotient. Let's finalize here by looking at a trigonometric function. So here we've got f at theta equals sine of theta minus 2 cosine theta. So just like we've done in our previous two examples, I want to start off to find the critical numbers by taking the derivative of the function. So that's going to be cosine theta minus 2 times negative sine of theta. And if I simplify, that becomes cosine of theta plus 2 sine of theta. And then again, to find the critical number, I take the derivative, set it equal to 0, and then I want to solve that. So what I'm going to do is I'm going to subtract over 2 sine of theta. It'll cancel from the left, and it'll appear here on the right side. So I've got cosine of theta equals negative 2 times sine of theta. And then to solve here, I want to divide by cosine of theta, which will make that left side have a value of 1. And then on the right side, I'm going to record negative 2, but then sine theta over cosine theta is equivalent to tangent of theta. And then I'm going to divide by negative 2. And we'll see that now I'm going to flip the equation around. Tangent of theta equals negative half. Let me leave a little room there. And then at that point, I want to apply inverse tangent. And that is my solution. So I should have a critical number when theta is the inverse tangent of negative half. So if I find an approximate value for that, So remember what inverse tangent is telling us. It's saying at what angle would the tangent ratio be -1/2. So if I just calculate that on a calculator, in fact, let me jump over to Desmos very quickly. I can just get an estimate. So inverse tangent is going to be under the functions tab of -1/2 is going to give me the value of roughly -0.4636. So let's write that down, and then let's come back to the graph here to see how are we going to locate these critical points. So it does have the value of about -0.4636. So I'll kind of keep my eye. That's really my critical number. But we got to go look at the graph to see, is that describing a maximum, a minimum, or neither? So let's go back to the graph, and I'm just going to remember here, what's my original function? What's my derivative function? So I'm going to type in the original, which is sine of, we'll use x here instead of theta, -2 cosine theta, or x. So that's the original function. Here's the derivative. G of x equals cosine x plus 2 sine of x. And we see that black curve is our derivative. So if I locate just that inflection, or that critical value at 0.4636, -0.4636, I can see that that does hit here right where the derivatives got a 0. And what it's associated with is a minimum value on the original function. And we can see that because the derivative's changing from negative value to positive value at that point. But that's only one out of many different critical points, because you can see it's a trigonometric function. It repeats over and over. So one thing we want to just check here is what's the period of the function. So I can just check plus pi. So it looks like from 0 to 0 is a period of pi. Now for the minimum points, those are going to be where this value of pi is multiplied by an even number. So this one is 0 pi. If I add plus 2 pi, that's going to take me to my next change where the derivative goes from negative to positive. So what we'll have to do is we got to write that there are repeated minimum values, and the way that those would be represented is either the approximate value, -0.4636, plus k pi, where k is an even integer. And then for my maximum values, because you can see the original purple function has both minimum and maximum. So the ones we've described with that k being an even integer are the minimum values of the function. If I change that value multiplying times pi to an odd number, so for instance 1, 3, even -1, -3, those are places on the function where it's got a maximum. The derivative's changing from positive to negative. So we can record that as -0.4636 plus, let's give it another name other than k. We'll call it j pi, and j is an odd integer. So with a trigonometric function, if you're not given a restricted domain, it is necessary to describe really the infinite number of each set of maximum values and minimum values. So our critical numbers there, what we need to just do is formalize what we're writing for the maximum and the minimum. So f of x has minimum values at, and let's write this in two different ways. So the approximate value is negative 0.4636 plus k pi, where k is an even integer. So we could write it like that, or we could write it exactly as the inverse tangent of negative half plus k pi, with the same k is an even integer. And then let's also say f of x has maximum values at, we could write it both ways again, 0.4636 plus j pi, and j is an odd integer. And just like we did previously, we could record that exactly. Inverse tangent at negative half plus j pi. Again, j is an odd integer. So we just have to be mindful with trigonometric functions that they can have infinite number of maximum and minimum points because they oscillate and they continue forever in that wave motion. Well, thank you for joining for this investigation of the first derivative test to decide are critical numbers maxima, minima, or neither. See you soon.